Welcome to APA's weekly webinar. My name is Billy Zydik, Manager, Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA webpage later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the webpage where all webinar recordings are housed, as well as a link to our upcoming webinars. We have webinars planned out through the end of 2021, and all are open for registration. Professional continuing education and AIA-CLU credits are being offered for today's program. If you're an AIA professional requiring a certificate, please send an email to me at Billie, B-I-L-L-I-E, @apa.org, along with your AIA membership number if you have not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, response will be sent directly to the person asking the question by our presenter. If you are just calling in, make sure to send me an email at billie@apa.org so I can send you a certificate if you requested one. The system only recognizes you if you log in. At this time, it's my pleasure to turn this over to Paul Shelton. I will rejoin you for the Q&A session later. Paul, take it away.
Thank you, Billie. Can you hear me okay?
I can hear you fine.
Okay, great. Thanks everyone for joining. I'm Paul Shelton from Alchemco. We are a manufacturer of concrete waterproofing products for exposed concrete structures. This does achieve one learning unit. It's also an HSW unit through the AIA. Sorry, my screen is not advancing. Sorry, Billie. Bear with me one second. There we go. Okay. Again, one full unit, HSW unit from the AIA. We're going to talk about waterproofing concrete structures, needs, benefits, options, what's available out there, and sort of why do we even talk about waterproofing concrete. Concrete is the most utilized construction material in the world, and it's very strong and it lasts for decades. However, it does have some aggressive conditions against it, and it does need protection in order to really live its full life. So understanding why we waterproof concrete for long-term structural integrity, the main causes of deterioration, the types of waterproofing applications that are available, and then we're going to compare within those types new construction versus existing structures. So again, for our table of contents, why is it important? The causes of deterioration, commonly used types of waterproofing, reduced maintenance and increased sustainability for new projects, and then a modified silicate gel versus a crystalline technology for existing concrete structures. And we will then go through some case studies and have questions. So why is it important to waterproof concrete? Concrete, again, is the most widely used construction material on the planet. It hasn't changed dramatically since its initial invention back in Babylonian times. In the 1700s, we started adding cement to that mix, and it really hasn't changed since. It's a very simple material consisting of cement, aggregates, and water. When the water is evaporating as concrete cures, it creates pores and voids as that water evaporates, and that makes the concrete permeable and porous. And this is a big contributing factor to why we need to waterproof. Those pores and that permeability allows the ingress of water and chemicals. In most cases, that water infiltration will not fix itself. I say in most cases, as we go through this, we'll cover, there is, according to how you treat the waterproofing, there are some ways that it can fix itself. And all too often, the attempt is there to waterproof, but really what they're doing is fixing the symptoms and not the problem. And what that does is actually causes more harm by moving the water, redirecting it to another spot, and then as the water collects in whatever that spot is, it starts to deteriorate. The rebar is where the actual problems come from. So there are many advantages to concrete as a building material. Number one, it's very low cost. It's non-flammable. It's eco-friendly. It has a great stiffness rating and compressive strength. It's easy to fabricate, and you can form it into almost any shape and type of structure. The disadvantages, however, are tensile strength, brittleness, and in its basic form, long-term durability. And I say in its basic form, meaning without waterproofing. So what we see is common symptoms of lack of waterproofing. Spalling is the picture in the left. We're going to go over that in more detail. Cracking, and then corrosion of the reinforcement bar or rebar. So as mentioned, it's permeable and porous. Permeability is the ease of which fluids can pass through. And porous is very similar, but is more describing how many and how large the pores in the material are. So if water and chemicals are continually allowed to penetrate the concrete, it will cause premature deterioration of the concrete. And some of those types of problems are spalling, stress cracks, freeze-thaw cracking, where the surface of the concrete has water and then freezes, chloride and salt penetration, hydrostatic pressure, and then corrosion of the steel reinforcement. And most all of this is caused because of allowing water to penetrate into the concrete. So it's critical to protect the concrete the right way. And now let's look at some of the factors that cause the deterioration. So the first is weather, mainly meaning rising and dropping temperatures and the presence of moisture. But it also this deterioration can result from improper mix design, from chemical interactions, flaws in the design, and then installation or construction flaws. So this is the middle picture is a water tank, and you can see the rebar is highly corroded and rusted. That's a chemical reaction. And then the picture to the right is an example of spalling, where concrete cracks from the inside out, and you can now clearly see the steel structure is completely rusted and deteriorating. Corrosion of the steel reinforcement or rust is the cause of spalling. And you see the pictures in the upper right. The first picture is healthy rebar. As that rebar begins to rust, it actually swells in size and it has nowhere to go. So it starts to crack the concrete from the inside out, and that is what we know as spalling. And that picture in the bottom is an example of spalled concrete. You've probably seen this before. Now that rebar is completely rusted and exposed, so now exposed to the weather, that deterioration is going to accelerate several times over. Carbonation is the presence of carbonic acid, which lowers the pH, which again is going to result in the same thing as rusted rebar and spalling. Chlorides have the same effect. Again, rusted rebar and spalling. This is an example of failing concrete due to improper design. This is an exit ramp from a highway, and it was not made to sufficiently handle the weight and shifting of traffic as the traffic goes by, and now you can see in the pictures, there's a large spalled area, and now the steel is exposed. And this also, this example did not properly plan for or address the shrinking and settling of the concrete. Some other things that can happen, and these are more relative to the installation or the construction. For example, too much water during curing, and that's, you see the picture of pitting and honeycombing, and then cracks on the surface. This is again relative to construction and installation. Not able to move properly causes cracking, and too much or too little tension can cause cracking. So concrete, again, it is very reliable. It's very commonly used, but it has a lot of strikes against it, trying to deteriorate it unless we select the proper way to protect it. So let's look at some of the methods that are used today for waterproofing concrete structures. So every method that is available to waterproof a concrete structure is either integral or inside the concrete itself, or it is non-integral, meaning it sits on the surface. So all strategies can be lumped into those two buckets, if you will. And while the intent is the same, keeping water out, the methods are widely different. So we're going to go over a very high-level summary of these. So first, we'll talk about sheet waterproofing or membranes, and these are either peel and stick, just like it sounds. You peel the back off of the sticker and then stick it on, and torch on, which means the adhesive layer is melted, and that's what makes it adhere. Then you have fluid applied membranes, both hot and cold. Hot being, I'm sure you've seen hot rubberized asphalt used on roofing. And then a cold fluid membrane is poured from a pail and then applied with a squeegee. Both of these, however, have a specific setup time. As they're poured out, or as the hot rubberized is melted, as it cools, it cures quickly, and it starts to thicken up and it becomes difficult to spread it evenly. Then your integral waterproofing systems, one is a crystalline technology, and the second is a modified silicate gel. And we'll cover all of these in a little more detail. So the sheet waterproofing or adhesive, it's exactly like it sounds, and you can see in the photo there, these gentlemen are pulling a backing off and trying to evenly roll this out with a properly prepped surface there to make sure that it adheres. One of the things that you'll notice here is in all cases of sheet waterproofing, there are going to be seams, and that is a common area where you might have a failure. The other thing to think about with this type of waterproofing strategy is any mechanical disturbance on the surface can puncture, tear, or delaminate, meaning it won't stick, this type of approach. So the challenges are the craftsmanship has to be very, very good. These folks have to be very good at applying this material, avoiding seams with leaks, making sure they overlap correctly. And if you can imagine trying to put this around a drain or around a corner or something of that nature, it's very difficult to get it right. And because they sit on the surface, there's a lot of forces against it that can cause abrasion or damage this material, and eventually causing it to either peel or become delaminated. This is the other type of sheet waterproofing. You can see there's a torch there melting the backing layer, and that's what's causing this particular kind to adhere. It has the same challenges, of seams, mechanical disturbance, things of that nature. And in many job or project applications, having an open flame is not acceptable. So again, craftsmanship is critical. Perfectly prepped area is critical. And there are a lot of factors that can work against this type of waterproofing strategy. Now, properly applied, it works great. But you can see there are challenges to get this right. This is an example of fluid applied. This particular one is a roofing material, is hot rubberized asphalt. And it's just like it sounds. This one gentleman is dumping the material while the other is spreading it with a squeegee. It's important here to have common thickness throughout. This will not have seams, which is an advantage. But as this material sets up, as it cools and hardens, it becomes more and more difficult to spread it evenly. So again, the craftsmanship, the skill involved is critical, and proper surface prep is absolutely critical, or this material can delaminate and not stick. This is another example of the same. So they're temperature sensitive as well. So on a cold day, this is going to set up much faster than it will on a hot, humid day in the summer. This is another example of the same, of fluid applied, spread with a squeegee, trying to get them as even as possible. And again, imagine putting this around a seam or into a corner or something of that nature. The craftsmanship is very, very important to get this right. This is also a fluid applied, and in this particular example, this is being sprayed on. Again, requires a certain level of skill, and in this case is going to require some very specific equipment. But even applied correctly, because it sits on the surface, it's subject to exterior damage, to delamination, to being cut, being torn, things of that nature. And even the weather can greatly interfere with this type of material setting up properly and adhering to the surface. So before we go on, I want to stress the fact that any material that sits on the surface, regardless of how expensive or how difficult or easy it was to apply, anything that sits on the surface is subject to mechanical damage, traffic, tearing, snowplow blades, things of that nature. So now we're going to look at a couple of integral waterproofing materials. So that means there would be inside the concrete, would be part of the concrete. This particular one is a crystalline technology, and it's just what it sounds like. It reacts with water and it forms little crystals inside the concrete, and those crystals plug and block every little pore, capillary, crack, little air pocket within the concrete. They will fill with these crystals. In the picture is the crystalline material being mixed into the concrete before it's being poured. So as the concrete cures and hardens and forms these little air pockets and these little pores within it, those will fill with these little crystals. And that forms a waterproofing layer and protects the steel from water and from corrosion. But it's just like it sounds. Crystalline is, it's like little shards of fiberglass, if you will. So it is a brittle approach. This is the same material. This is a different way to apply it. In this case, they have freshly poured concrete. So that concrete is still full of water, still wet. And they're shaking the crystalline on the surface. You can see in the picture, just like confectionery sugar in a bakery. And the crystals react with that water, and that causes it to penetrate into the concrete and form those crystals. Again, blocking micro cracks, pores, capillaries, any little opening within that concrete. Crystalline can also be applied as what we call a slurry. So it's mixed into a cementitious mix within a pail or a bucket, and then brushed on. In this case, you can see this gentleman's using like a broom to brush this on. It's important to understand here, anytime they use a slurry, it is going to change the surface of the concrete. So in some cases, that is not acceptable. Here's another more detailed picture, and you can see exactly what that's going to look like. It's going to have paint strokes. It's going to change the surface of the concrete dramatically. It is a very effective strategy. This is a good material. But if you're doing, for example, a historic structure, this would not be acceptable. This is an example of a spray-applied modified silicate gel, and you see the word flexible here, and this is key. I mentioned with the crystalline that it's like shards of fiberglass. It is a brittle material. So if I'm waterproofing a structure like a parking garage or a bridge that has a lot of movement, that crystalline material is not going to be as flexible as a silicate gel. And it's just like it sounds. In a glass, it looks like the old Elmer's paste. It's a soft material, and it's sort of like putting a membrane inside the concrete about an inch deep, if that makes sense. That's what the modified silicate gel, that's how this material will work. And like the crystalline, the silicate material reacts with water, and it forms the gel, blocking those capillaries, those pores, any little microfractures inside the concrete. But this time we're filling it with a soft, flexible material. It is clear and odorless. It's safe. It's a green material. And it's key to understand that it does not change the surface of the concrete. Once that material penetrates inside the concrete and it is dry, it will look just like concrete. And if you remember earlier in the presentation, we mentioned that concrete cannot self-heal or heal itself once it's leaking. These two materials, crystalline and silicate gel, these are the exceptions where the concrete can, quote, heal itself. Because they react with water, now we've taken a foe and made it our friend in terms of the concrete. Water is very bad for concrete. In this case, whether it's crystalline or whether it's a silicate gel, when water becomes present, it's going to create more of that waterproofing layer protecting the concrete. And in both cases, we now have an integral waterproofing system. And if you recall, I mentioned anything that sits on the surface can be damaged. Both of these are inside the concrete. You cannot damage them. It cannot be torn. It cannot be scraped off. It can't delaminate. It actually becomes a part of the concrete matrix, either of these solutions. This is a picture of the crystalline material under a microscope growing into a pore. So just like I mentioned, like little shards of fiberglass, it just fills that pore up. So we've talked about integral versus surface applied waterproofing. We can also look at new concrete structures versus existing concrete structures. So in this case, the crystalline material can be applied three main ways. Number one is to surface apply the slurry using an air compressed sprayer or by brooming it on like we saw in the previous pictures. Secondly, the dry shake method is where we broadcast crystalline material onto the surface of freshly poured concrete. Most commonly, it is incorporated into the concrete mix, either at the concrete plant or in the concrete truck on the project site. So for example, if a truck has 9 yards of concrete in it, you're going to put sufficient amount of crystalline at the job site into the truck, spin it for 10 minutes to mix it, and you're ready to pour. One big advantage of this is there's absolutely no craftsmanship involved. So it adds zero labor cost, and in a sense, they can't mess it up. As long as they have the right amount in the concrete, they just pour concrete as normal as they would have without waterproofing. So there are many things are called admixtures. Some speed up the hardening process, but in this case, we're talking specifically about crystalline that is made specifically to waterproof the concrete. It reacts with free lime in the mix, and the active chemicals combining with water create these insoluble crystals that penetrate deep into the concrete and form that waterproofing layer, block the passage of water, and keep the rebar from rusting. So rather than adding waterproofing after a structure is built with an admixture, we're putting it right into the concrete. So we're taking what normally would be very permeable and porous, and we're blocking those pores with this waterproofing barrier to prevent corrosion. So again, kind of restating the same thing here, this is not subject to craftsmanship or workmanship. They're going to pour the concrete as they always have. It is VOC free, and it's important to keep in mind that that concrete is completely recyclable after that structure has reached its useful life and is torn down. It can go into a landfill and it's safe. Cannot be torn, cannot delaminate, will never wear out. So it's in that concrete for the life of the structure. These are some of the types of structures where crystalline admixtures are used: slabs and walls, foundation, water storage tanks, basements, elevator shafts, parking garages, swimming pools. So that was new construction. So now we're going to look at existing structures. So how do we waterproof and protect an existing structure? And in many of the universities, there are multiple parking structures. We see here a modified silicate gel being spray applied and a crystalline slurry being brush applied. So again, existing structures. These are three photos of the crystalline, or I'm sorry, of the silicate gel being applied. And this is how simple it is to apply the silicate gel material. This is a small structure, so they're using a small backpack sprayer. In a larger area, they would use more elaborate spray equipment directly from the drum, and it would spray much faster. This is an example of spraying from the drum. And as you can see, it's just a simple water hose with a sprayer on it. And you can see how much faster this gentleman is covering the area than was previous with the backpack sprayer. And it's important to note here too, you see traffic going by. That would not be possible if this structure was waterproofed with a coating that was applied to the surface. This is another example of the same. This is the watering in, they call it. Water is applied to help the silicate penetrate into the concrete, but also importantly to start the chemical reaction. As we mentioned before, it reacts with water. So this is actually part of the application process. Very simple, not any real dramatic craftsmanship involved. And so this is the crystalline slurry. Two ways to apply this is number one with some elaborate spray equipment, and number two is brush applied like we talked about before. So these are for existing structures. Both are integral, so cannot be damaged. There are no seams, low overall cost. It can be applied on negative or positive side. And what that means is, for example, let's say we have a building envelope or a foundation of a building. The positive side would be where the water is coming from. The negative side would be, for example, inside a basement. So these can be used on either side. It is always advised to do the positive side where the water is coming from. However, it can be applied on either side. Both will protect the reinforcing steel from being corroded or rusted, and this is critical. If our steel does not rust, we will not have spalling that we saw earlier. You still may have some concrete wear issues, but spalling you can basically eliminate. Both are environmentally friendly. They cannot be compromised by poor site conditions or craftsmanship. They cannot be damaged. Both of these types of material are have long time wonderful track records within the industry. Both are well over 30 years in existence. Friend becomes foe that we mentioned before. Unprotected concrete is damaged by water, where with either of these solutions, water simply makes the waterproofing react so that it protects the concrete. Both of them leave chemicals behind in the concrete, and every time water becomes present, they react again. So these products are different than a simple densifier in that they will actually waterproof the concrete. They remain dormant inside the concrete until water shows up, and then it activates again, creating that waterproofing layer. So you really can have a one-time permanent waterproofing applied to the concrete. Both of these systems are very resistant to hydrostatic pressure or water pressure. So things like dams, subways, tunnels, those are great applications for these types of products. Both of these do require proper surface prep before they are applied. Now, specifically, the modified silicate gel has some additional advantages over the crystalline. Number one, it's a very fast, easy install process. So those videos we saw spraying with the hose and a sprayer, that two-man crew will cover about 15,000 square feet per hour. And it would probably take that crew a full day to do 15,000 square feet with crystalline. They may not even be able to do half that. So it's a huge advantage in terms of the downtime of the structure to use the modified silicate gel strategy. Again, very simple to spray, absorbs into concrete. And another advantage over the crystalline is leaving the concrete surface unchanged. So again, historical structure, visible structure, things of that nature, where they don't want to change the appearance, the crystalline slurry would not be an option. They would be better suited with the silicate gel. Also, the surface of that concrete can still be painted or applied a coating for aesthetics, or for slip resistance, and it will still adhere just fine even though the silicate gel is within the concrete. So in addition to being fast and easy to apply, the equipment is very, very simple. You don't have expensive, elaborate equipment required to apply a silicate gel strategy. And another big advantage is both of these strategies will heal cracks as they start to form in the future. So I mentioned the chemicals stay behind and are activated by water. So let's say we've waterproofed a concrete structure and 5 years later a crack begins to develop. As soon as water is present, up to 0.4 millimeters, these materials will fill that crack and continue to waterproof. But specifically with the modified silicate gel, on initial installation, they will actually heal a crack up to 2 millimeters wide. And that's a significant crack. That's about like looking at the width of a car key, like the top of a car key. That's much larger. That's 5 times bigger than a crack that the crystalline can heal. Another advantage is that the silicate gel strategy will increase the hardness of the surface of the concrete from 6 to 8 on the Mohs scale. And if you're not familiar with that, 8 is the equivalent of granite. It's like taking 3,500 PSI concrete and making it the equivalent of 5,000 PSI. So that is an advantage to limit surface cracking and to limit wear. So a bridge or a parking structure, that concrete does actually wear a small layer off. And then finally, crystalline, we mentioned earlier that it's brittle, so is really not ideal for a structure that experiences a lot of movement like a bridge or parking structure. In those cases, a silicate gel is a much better strategy because it's flexible. It can move with the structure. So pros and cons, really the only con to use the silicate gel is that the surface must be clean and dry for application. Where with the crystalline slurry, a wet surface is acceptable. But the pros, fast, easy, very simple equipment, extreme hydrostatic pressure resistance, becomes integral, remains reactive, will heal a 2 millimeter crack on install, and in future will heal a 0.4 millimeter crack as it begins to form. It allows outgassing. And what that means is, let's say we're waterproofing a parking structure, and we know it has received water in the past that's going to rust the rebar. If we apply a silicate gel, no more water can get in, but the water that's trapped can evaporate. So over time, that rebar will become completely dry. It's highly resistant to chemicals like de-icing salts. It's non-toxic, VOC-free, completely recyclable after demolition. You cannot puncture, tear, or pull apart at the seam. You don't lose any slip resistance that concrete naturally provides. There's no priming or leveling required like with some coatings. There are no seams, no overlapping, no corners or edges. Can apply to positive or negative side, increases the hardness of the concrete surface. Low cost, not subject to determination or wear, and it actually increases the bond strength of the cementitious materials. So a lot of pros for the silicate gel strategy. Advantage of crystalline is it can be applied as a slurry, above or below grade. It usually is a couple of coats for the application. It prevents water from penetrating. causing a catalytic reaction that produces this crystalline formulation that fills the pores and keeps the water out. So, like the silicate gel, resistant to hydrostatic pressure, is integral, can heal some future cracks. It also allows the concrete to breathe, resistant to chemicals, non-toxic. One advantage is it does not require a dry surface like the silicate gel does. Cannot be punctured or torn. No surface priming or leveling. Does not require any finishing. Can be applied positive or negative. Couple of cons are it will change the surface. It's a slow, labor-intensive process. And if you do go with the spray method, that is very specialized equipment. Should not be used on structures with significant movement. And it does require a couple of coats, in most cases at least 2 coats to use this. And so that's really all of the presentation, but we have here some case study examples. This is a case study where the crystalline admixture was used. This is a soccer field that is actually sits on top of a parking structure. These are cooling towers. And this is, now we're talking about the silicate gel. This is the Lowe's headquarters in North Carolina. A number of parking structures there have been treated. Miami International Airport, over 700,000 square feet of parking structures there treated. Very difficult environment. The planes actually take off over these parking structures, spitting burnt jet fuel on them. And with the silicate gel being in place, the fuel can't penetrate. This is at Pitt University. All of the areas you see around the Peterson Event Center, the stairs and all the concrete decks were all treated. Several resorts, parking structures at resorts in Miami Beach, or I'm sorry, in Myrtle Beach. This is Paul Brown Stadium where the Cincinnati Bengals play. That area directly in front of you is where trucks pull up to load and unload, and had significant cracking, and the silicate gel was applied there. This is actually a man-made concrete pond that sits directly over an underground parking structure. And that concrete pond holds water. It even holds living fish. We mentioned that the silicate gel is harmless. This is a project that was applied in '88, and every 8 to 10 years, we have had third-party companies do water tests over where were leaking cracks. And what you see there in the picture is little PVC tubs caulked to the crack, filled with water and monitored. And over 30 years later now, without being reapplied, those cracks do not leak. Significant example of the effectiveness of the silicate gel strategy. 3 or 4 hospitals in Atlanta on their parking structures. This one was balconies, parking, and walkways. This is actually a terminal in Brazil that sits in the ocean in salt water that was treated with the silicate gel to protect it against corrosion. And salt water is about as harmful as you could possibly apply to concrete, and it has not deteriorated and is 100% watertight still today. Over 1 million square feet of runway at the Pittsburgh International Airport, and you can see the spray rig at the bottom that they created to apply the material faster. Has several spray nozzles on that piece of equipment. The entire water park in Bahrain, every pool in this park was treated with the silicate gel over 200,000 square feet. This is the basketball arena at Fort Collins, Colorado. Hatfield and McCoy Dinner Theater, that is an Olympic-sized diving pool that's part of their play that was badly leaking and was treated with the silicate gel and completely watertight. This is a soccer stadium in Italy, and we mentioned that you can still coat or paint after using the silicate gel. These concrete stands were treated, and then you can see that they've been painted. Over 160,000 square feet of concrete. Another hospital in Atlanta, 1 million square foot of, this was a new bridge treated with the silicate gel and then poured asphalt for the drive lanes over top of the concrete structure. So in summary, there's a lot of ways to waterproof concrete. We've talked about why we need to do it in order for the concrete structure to actually reach its full life expectancy, and compared a couple of different ways to do it. So thank you all for joining. Really appreciate the time and attention. And if you have any questions, we can go over those now.
Okay, Paul, you have quite a few questions. So the first question is, does this waterproof only concrete surfaces, or will it also work on brick surfaces?
Okay, very good question. There is a very similar, it's basically the same, same type of chemicals. It can be applied to a brick wall. Now, brick is clay, so it's a little different. The material reacts with free calcium in the concrete. That's what makes it form that gel layer. So the difference is, on brick, it would have to be reapplied every so often. It wouldn't last the life of the structure, but it would work. It would still waterproof. However, in a brick wall, what normally deteriorates and leaks is the mortar. It's not really the clay. Now, the mortar is cementitious, and this material does a fantastic job of waterproofing the mortar. And if you've ever experienced tuck pointing, is when they have to go in and scrape away all the deterioration and reapply mortar. This would prevent that from having to be done. Not only does it waterproof that mortar, but one of the things you may have heard me mention earlier, it makes cementitious materials adhere together better. So that mortar is not going to deteriorate the same if this material is sprayed onto it. Very good question.
Okay, thank you. And of course, our attendees are asking if you will be willing to share your slides with them today.
Absolutely. Can I send those to you, Billy? Is that the best way to do that?
That is the best way to do it. And then they can reach, everyone will get a follow-up email from me tomorrow. And if you would like the slides, they just need to respond to me that way. So thank you so much. Okay, our next question. Your first slide had an image of the Solomon R. Guggenheim Museum. Was one of these crystalline products used on that building?
It was the spray applied silicate gel.
Okay, thank you. And someone is asking, will the product work on plaster?
Good question. What I would need to know is the chemical makeup of the plaster. If it has limestone, then this might be a good solution for that. I'd need to know a little more about the plaster.
Okay. Well, you'll get the question, and you can reach out to Greg to get more details on that.
Great.
So the next question is, does the silicate gel used on concrete walks, benches, tables, and pavers inhibit surface mildew or other organic discoloration?
Okay, very good question. The way I would answer that is, the way the gel is formed, it does soak up water. So for example, if the silicate gel has been applied to pavers and those pavers are dry for, let's say, a couple of months, then the material is just sitting there dormant. But as soon as water becomes present, that water will form the gel again. And so where I'm going with this is that means there is a little moisture in the gel. It can't get in the concrete, but in the gel itself, there's some moisture in there to make that gel. So whether that would cause mildew or not, I can't really say. What I can say is if it's present at all, it would only be on the surface and could be easily cleaned off. It could not grow mildew into the concrete like you may have experienced before.
Okay, thank you. Next question. What about using modified silicate gel in swimming pools? How often would it need to be treated?
Okay, very good question. Keep in mind the concrete must be clean and dry for the application. Now, let's say that we have an existing pool, we do the prep to get it nice and clean and dry, apply the silicate gel material, it would never need to be reapplied. Now, keep in mind you may have joints in the corner. Now, that's different. That would need a bead of caulk and something like a flashing material applied over the caulk. So you treat the joint a little different than you do the slab per se. If it was one continuous pour without joints, you wouldn't need anything but the silicate gel. And because it reacts with water, especially a pool, it is constantly active. You would never need to reapply.
Okay, wonderful, thank you. Now, our next question is, could this product be used on an SMU wall?
It can be used. The problem with SMU is it's even more porous than traditional concrete. So it will still provide the protection if there's rebar within there. But I don't know that we would warrant waterproof per se. And I'll give you a little more detail on that. We did some CMU just for curiosity. We did a typical application and it did not waterproof it. When we did a water test, the water leaked. We applied it repeatedly and we did get it watertight. However, if you have to apply it 3 or 4 times, now your cost has also gone up ×4, and I don't know that it would be cost effective. But if the client is just looking for, quote, protection, absolutely it will help protect that structure.
Okay, thank you. We have our next question is, what happens if the first water the concrete is exposed to is mixed with salt, i.e. the crystalline hasn't had an opportunity to react with just water only?
So if I understand the question right, so the very first presence of water is salt water? Does that sound right?
I will ask for a clarification on that, and we'll come back to it.
Well, I'll answer it that way, and if that's the case. Okay. As I went through the slides of the silicate gel, I mentioned that one part of the process is watering it, applying water to push it down into the concrete. That water can be salt water, and it will still be just as effective. Now that's the silicate gel, so the crystalline is a little different, but the presence of water activates the chemicals. So initially the thought is it would protect it just as well whether it was fresh water or salt.
Okay, and our next question is, can this product be used on a rock wall water fountain?
So it will not penetrate the rocks themselves, but if the rocks are in concrete, it still offers protection. The example I will give is aggregate sidewalks and driveways. You may have seen how in aggregate driveways and sidewalks, the little rocks, the aggregate, eventually pop out. And we have seen applications where the material was applied. Keep in mind, I mentioned the cementitious materials hold together even better. So what happens is the aggregate no longer pops out, because what we've waterproofed is the actual concrete around those aggregates. So it'll hold the aggregate in, and it won't penetrate the stone itself, but all around it will be waterproofed, if that makes sense.
Okay. And I did get a response back, and you did answer the question regarding the water and the salt. So
Okay, great, great.
And the rest of our questions are better answered offline. I will send these over to you, Paul, to answer these individual questions. So at this time, I would like to say thank you so much, Paul, for filling in for a fellow coworker who was not available today.
My pleasure. Thank you very much for the opportunity, Billy. I really appreciate it.
Not a problem. And to our attendees, as always, thank you so much for taking time out of your busy schedule to be with us today. And as always, be safe, stay healthy, and be kind to one another. Thank you. Have a great day. Bye-bye now.
Bye-bye.